so many of your faces, especially as I know so many of you have been studying hard for the upcoming mid-semester test. Don't worry, you're all going to get through it one way or another, even if I have to drag your corpses off the floor tomorrow.
Jesus.
Don't worry, it'll be fine, I'm just kidding. So turning back to yesterday's conclusion, we looked at algorithms for searching for a name in a set of different objects. In our case yesterday, we were looking through the phone book to find a given name in a very, very long list of names. Now, while we did find a more efficient way of searching through to find our name Cohen, it relied on a crucial property of the white pages. Does anyone have an idea why our second method actually worked?
So the entire list is sorted.
Yeah, so Xinjiang said that the reason why we were able to do our efficient method of like breaking the phone book in half and deciding which half the thing was in was because it was in order. This meant that we knew by looking at where we were, in which direction to go. However, most of the time when you get data, it doesn't start off sorted. That's an operation that you actually have to perform and that we looked at last week with bubble sort and insertion sort, with more sorts to come, that enabled us to do this most efficient method. But what happens if we still want to do the search and we don't have time for sorting? Or if our list of items is small, how can we still find the thing we're looking for? So this takes us back to our original algorithm, linear search, going through the items one by one until finding the one we want. This does work on a sorted array, but crucially, it also works on an unsorted array. That makes it a little different from binary search that we'll explore either later today or early next week. The intuition for linear search is that if the array isn't sorted, in the worst case, you really are going to have to look through everything. Because if the item you're looking for is the very last item, well, it makes sense that you're going to have to go one by one by one by one, because you don't know where it is. It could be at the middle, it could be at the beginning, it could be at the end. So in the worst case, you are going to have to look at each and every item. This is the pseudocode, or a sketch of linear search. And we have our two questions from yesterday. Remember, the third one we're leaving out. The two questions are, is it correct and is it efficient? In today's lecture, we're going to go over proof techniques to answer both of these questions. The way the algorithm works is it sets some counter to 0, and we're going to get used to looking at these sketches. It sets a counter to 0, and the counter is going to increment as we go through each index of our array. Assuming that our array is of length n, this means that I is going to go from 0 up to the length of the array minus 1. Remember, because if an array has 7 items, the indices are from 0 to 6, and so we're going to look at items 0 to 6, and so our index variable I should also range from 0 to 6. So while I is doesn't exceed the bounds of the array, and AI, where A is the array we're looking at, and the index I, if the item we're looking at is not the one that we want to find, and we'll call this X, move to the next item. So again, A is our array, I is the index of the array, and X is the item we're looking for. If you haven't found the item yet, and the current item is not the right one, move to the next item. Seems like a pretty reasonable thing to do that you can come up with even on your own without necessarily this pseudocode sketch. The reason we're using this pseudocode sketch, though, is it's going to allow us to prove certain facts about this process. Then we have our next check to see if we've actually exceeded the bounds of the array. So if you get to the very end and your array index is past the end of the array, if you've already incremented to, say, it was length 6, and if at the end I has been updated to 7 and the while loop fails and so you exit the while loop. So if I is equal to 7, return not found, because if we're outside the end and we didn't stop, then we haven't found the item and we're done. On the other hand, if we did find the item early, that means I will never have gotten all the way to end because that while loop would have finished early. In this case, our function overall can return I being the index where we stopped, because we know that the index where we stopped is the index where the item X was located. The reason being is that we know that was when we would have exited the while loop. So let's actually prove the correctness of this, and it's going to be just a slightly more formal way of saying the same thing I did, but that using tighter mathematical reasoning will actually make it a little easier and give us a clearer language with which to explain these same concepts. Given that explaining it in terms of like English language can be a little tricky, it's helpful to have a syntactical language and a different way of making the same arguments. Because a mathematical proof, the goal of a mathematical proof is to convince the reader. So a mathematical proof can be written in English, but that might be substantially less convincing because it will leave out elements, leave things unsaid, or leave things unclear. And this is why we're going to turn to using invariants to solve things. Not because you can't prove the runtime of something another way, and not because you can't prove the correctness another way. It's because the mathematical language is particularly concise and effective at conveying to someone else the strength of our argument and the content of our argument. Here is an example of one form of notation. And so we're designing a loop invariant that'll hold over the course of the lifetime of our while loop that we can then use to make the argument that our function is correct. So let us just create an invariant out of thin air. You'll understand later how one might come up with your own invariant, but for the time being, let's just take this one as a given. Let's define our invariant, and we'll call our invariant P, and that fancy 3-line symbol is just saying that this is a definition for P. So I'm going to give you this definition, and the definition is that I should always be between 0 and n inclusive, and that x should not be between the 0th element of the array up to the current index of the array minus 1. So if we're currently looking at array index 3, our invariant says, take it as a given that the element x that we're looking for is not in 2, is not in 1, is not in 0. So that's our invariant. It's the combination of these two claims. Now we don't know if it's true yet. We're going to have to check it. But if we can show that this invariant is true throughout, it might actually lead us to a conclusion of what we're trying to prove, which is that our algorithm is correct. Here is the overall a copy of our prior algorithm, only this time I've added some assert statements. Assert statements in this case are just being used to remind us that at this point in the code, in order for our argument to work, we should check the thing next to the assert, and if the assert fails, our proof fails, and if the asserts are correct all the way through, hopefully that should give us a stronger argument that our function is correct. Let's break this down a little more. Taking the first chunk, this is the same as our pseudocode from before, only with some assert statements. And let's check P at each of these different stages. Remember the statement P was that I, the index, is between 0 and n inclusive, and that the array element that we're searching for isn't in the ones that we've already seen. So let's check it at the beginning. Set I to 0 is, remember that the first chunk of our statement P was that I is between 0 and n inclusive. Is 0 between 0 and n inclusive?
Yes.
Yes? So we move to the second half of our assertion statement. The second half of our assertion statement is that between 0 and I minus 1, the element that we're looking for isn't there. Is the element already there before we've even started the array, the one that we're looking for? No, so our statement is true. It is not the case that we've already seen x, and it is also the case that we're within the bounds of the array, I is 0. Now let's move to the next line. It starts our while loop, so we can move on again and go to our next assert statement. Is our assert statement still true? Is it still the case that I is between 0 and n? Yes. Is it still the case that we haven't seen the element that we are looking for? Yes. How do we know? Well, we never would have entered the while loop if it turned out that a of 0 was x. You can see that at the start of the while loop there is a check making sure that a0 does not equal x. If a0 did equal x, we would have finished and we never would have reached this assert statement here. That second one in the list for those of you on Zoom. So that assures us that P is true, and then we have this other half of the assert statement. Is I less than n? Well, for sure, because I hasn't changed yet. And we know that AI is not x, that's the other half of our assert statement. Does anyone see the difference between P and this statement on the second half? It's a very subtle difference, it's slight. So the second half of our assert statement looks just like P again with one small difference. Can anyone see it?
They're equal.
Yeah, great. Yara, do you want to say that into the microphone for everyone?
They're equal.
Yeah, so in this case, instead of it being I less than or equal to n, this time we're saying that I is definitely less than n. Why are we doing this? Well, we want to show that we're not outside the array, our while loop hasn't terminated. And remember, if I was equal to n, we wouldn't have entered this while loop, and so this gives us something a little stricter that we can say. While we're inside the while loop, we know that both of the while loop's guards hold true. So this gives us a stronger statement than we had before. Now we increment I, and we check our statement again. Is it the case that we are still within the bounds of the array? Yes, because even if we've now reached, say, the 7th element in a 6-element array, remember that n is the size of the array. Oh, sorry, let me backtrack that a second. If our array has 7 elements in it, and we're at index 7, we're outside our ability to access an array because I is larger than 6, which is the maximum index. But P, remember, had this less than or equals to sign in it. And so I is still less than the size of the array, even though it's exceeded the indices of the array. So P is still true, even when we increment I, and even when that particular increment was the one that took us past the largest index in the array. So that's still true, and we also still know that we haven't found X. So we run this again. Now I is equal to 1, and let's do this check again. Is 1 still, for our array of length with 7 items in it, is 1 less than 7? Yes. And is the current element the one we're looking for? Let's assume that the element is not in the array at all. So it's obviously not the one we're looking for because it's not in the array, and we go on and do this again. And the same reasoning applies for both of our assert statements for why the first assert statement is still true, because we're still strictly within the indices of the array, and we know we haven't found the item yet because it's not in the array, and we can keep doing this over and over and over. And at the end, once we get to, let's say I is 6, I plus 1 is 7. 7 is still less than or equal to 7, but now when we get to the while loop the next time, it's not actually going to run because 7 is not strictly less than 7, so we never enter the while loop. Instead, we get to this second half, and we're just going to focus on this first not found chunk, and then we're going to repeat again in the case where the item was actually in the array. So assert P, remember this included the inclusive less than or equal to, so P is still true. It's not the case that we have already seen X and we are still in the array. And now let's look at this other one. And I is greater than or equal to n, or AI equal to X. So we know that this part isn't true because the element was not in the array. And we know that this is true, I is greater than or equal to n, because we reached the very end of our array. And so is 7 greater than or equal to 7? Yes, it is. Now, what would have happened if we had found the element? This wouldn't have been true. I would not have been greater than or equal to n because we would have stopped part way. However, our or allows this other half to be true. We would have found it, and so overall this statement would have been true. Now let's go to our next line here. If I is greater than or equal to n, which is the case if the element wasn't found, do our assertion from before, which we know was true because we just looked at it and nothing big has changed. And we know for sure that I is greater than or equal to n. If this whole thing is true, logically that implies that AI equals X must be false. Why? Because we know that at least one of I is bigger than or equal to n must be true, or AI equals X must be true, and because only one of them can be true, and we've said here for sure that this one is true, that means that that one is not true. Which gives us, as a result, that X is not in the set of elements contained in the array, and we are now assured of the correctness of our algorithm when it returns not found. Now let's run this again for the case where X is an element in the array. if x is in the array, we've started running it a few times over, and our assertions follow as before. But now, at some point, we hit a block, and ai is equal to x, and the loop doesn't run, and so I stops growing. Now remember, our assertion statement, let's go back. Our assertion statement P is that x is not one of the elements before the index that we're currently looking at. So it does not include the current index. It just says the stuff that we'd seen prior. And so our assertion isn't validated if the current thing we're looking at is the one we wanted to find. Let's say we're at index I equals 2, and the element we're looking for is at index 2. Our assertion statement says that the element x was not at index 0 or index 1. So our assertion statement is still true even when the current thing that we're looking at is the one we're looking for, and our index of I reflects that. We know we now exit the loop, and we run our assertion statement again. We just said this was true. Our value of I is within the bounds of the array, inclusive of the endpoint. And it's also the case that the items before the one that we're currently looking at were not the one that we were searching for. We know this because of our proof in the prior part of the algorithm. So now we go back to our if statement. Is I bigger than or equal to n? Is this true or not? I is not bigger than or equal to n because we didn't go all the way through the array. We stopped early, and so I stopped getting bigger, and at some point I stopped at index 2, which was the array index of the thing we were looking to find. This means we jump to our else statement. And notice that our assertion now is slightly different from the one over here. It's the same P, which we know is true because that's where we stopped and we've been repeating it over and over again, but we've got this second half. It is not the case that I is bigger than or equal to n. How do we know this is true? Well, we're in this branch of the if, and we could not get to this branch of the if this were true. And if this is not true, and this assert over here is true, that means that as before, at least one of I is bigger than n or ai equals x must be true. And we've just said it's not the case that I is bigger than or equal to n. This leaves us with only one conclusion. ai, so the current thing that we're looking at in the array, must be x. Putting this all together, we now have a complete set of assertions that give us confidence that regardless of which way this program ends, it is going to end in the correct result. The correct result being, by definition, if the element x is in some index I between 0 and n minus 1, then the value of I at the conclusion of the function should be the value I, where I is the same index at which x is located within the array. This shows us how simple assertions that may seem tedious to repeat over and over can actually be quite powerful in helping us build up an argument about the correctness of an overall algorithm. Bringing this back to your actual C programming, you can include these proof techniques to give yourself confidence that your code is working. This is slightly different from a mathematical argument, of course, because your C code, you probably don't annotate with mathematical proofs the whole way through, but you can use the same kind of technique of assertions to give yourself assurances and give other programmers assurances that your program is functioning as expected. So inside assert.h, and if you type in the man page's man assert, you'll see these details. There is in fact an assert statement in the C language. And this allows you to do similar things to, in your C program, include assert statements that will cause your program to end early with an error if the assert is violated. So if you were to write linear search in this way, and you get error message, assertion failed, you could be confident that either you've designed your algorithm wrong, which we know we haven't because we've seen this mathematical proof for linear search, or you've actually made a mistake in your code. Now we do have a question from, no? Answer the question. Any other questions now while we're taking a second? Yeah. Okay, we've got a couple questions. Vincent, do you want to pass that back?
Just for the second part of the program, that needs to see if it's in the array. I think the I only needs to the maximum possible value for I is to equal to n, right? Because it can't get bigger than n because it's I plus 1
Yeah.
maximum, which is the length of the.
That is correct. The maximum possible value of I is equal to n, but n is bigger than or equal to n. So if we go back a slide or two. Whoop. See in our assertion statement there, it's not I is less than n, it's less than or equals to. And so if I equals n, then that is still true.
Okay, yeah.
Sorry, Albert. Did you have a question as well?
Just a quick one. It's just that
On assertion statements, you're just adding more if statements as it iterates through the loop.
So you can add more if statements and then just make your program exit if the if statements are false. Asserts are treated specially by programs that analyze programs. So there are programs called static analysis tools that look at your program and analyze what you've done. And so firstly, they'll single out assert statements as indicators of important things to look at. And we can talk more about that a little later. And also there's a simple and easy way that the compiler allows you to turn assertions on or off. So if you've written code for a customer and you don't want the code to break, but you want to be able to debug it easily, you might turn assertions off to save the computer wasting time and energy checking things when you know your program is correct. And then when a bug occurs, you might turn all the assertions back on again to see where things are failing.
Thank you.
No worries. Anything else before we move on a little bit? Let's go back to our runtime analysis for linear search. Given whatever set of elements in the array you like, and whatever x you choose, so you get to choose what x we're looking for, and you get to choose what items are in the array. There's our code. What is the minimum number of comparisons that we have to make in order for this program to terminate? That I didn't hear. Was it Fox? Remind me your name. You gotta say it in the microphone. And do you want to explain how you'd set up your array and your value of x so that it's 1?
yeah, it's the same.
Well, you hold the microphone. I'm asking you now. So when does the program finish? When are we finished with linear search? You got to hold the microphone up, otherwise no one will hear you. Either when the array ends, or what's the goal of the algorithm? Find what you want to find, exactly. So if you... No worries. Okay, you guys want to handle the rest of this one? Okay, so how do we know if we've found what we want to find? What do? What do we check?
We check the assertion.
Yeah, we check if the current element is the one we're looking for. And what is the minimum number of times we want to do that? You said it's 1.
Yeah.
In what case do we only have to look at one thing? Yeah, so when the very first thing in the array is the element we were looking for, that's our best case. So the very best case of linear search is in our first step we get lucky and the thing we were looking for is the thing we were trying to find. What about the worst case? If we have an array of n elements,
You then search through like the entire array. Oh, my name is
Yeah.
Craft. Yeah. So basically you go through the entire array. So it's just like O(n) time.
yeah, it's O of n time because the worst case is we look at every element in the array and the item we're looking for is not there. So we've spent a whole time looking at every single thing. Is it you? Is it you? Is it you? Is it you? We're wrong every time. And so we have taken a minimum of n steps, or n comparisons in this case. And in the average case, if we were to fill this with totally random elements, and let's say in this case, we guarantee that one of the elements is the one we're looking for. If we do it randomly over and over and over again, in expectation, how many steps is it going to take us? Anyone have a guess?
N over 2.
Yeah, n over 2. Xinjiang, do you want to explain why you think it's n over 2?
Like if the array is completely random and there is 1 and the item we're looking for over 2 times of comparison.
Yeah, that's the right answer, because if we make the array totally random, there's an equal chance that it'll be at the beginning as at the end, so those probabilities cancel each other out in terms of if we have to go all the way to the end and all the way to the beginning, in average, if it's only one of those two options, and it's equally likely to be either the first one or the last one, that would give us n on 2. Now let's look at the second last one and the second one in order. If they're also equally likely and we sum the average of those up, that'll also be n on 2. And so on and so forth for all pairs of items in the array. Because every item is equally likely to have the correct element, on average we're going to have to look at half of them, because half of the time it'll randomly have been put in the far half, and half the time it'll have been put in the near half, and it's just going to cancel out in expectation over the entire array. So that gives us our analysis for our very first formal analysis of an algorithm. We can always hope for the best. We can hope that the thing we're looking for is the very first item that we look at, but it's probably not the wisest plan. We could also plan for the average case, which might be a little more reasonable, but we should know that the worst case might actually happen and that our code probably shouldn't fail spectacularly if we hit that worst case. Why should we worry about the worst case? I mean, on average, we're not going to hit it. Well, the computer accepts input from individuals who aren't necessarily entirely altruistic. Say you are running a program at Facebook, a search algorithm at Facebook, and someone consistently enters into their newsfeed something that they know will cause the search algorithm to go all the way to the end. And they keep doing this over and over and over, making you search through things over and over and over. Your overall program is going to run pretty slowly. And so for any program that accepts user input, you've got to be really careful, because you are not the only one who's going to be entering input into the computer. There are other potentially malicious individuals who will have access to your program as well. And even if we exclude the malicious individuals, if you aren't confident that you're not going to hit the worst case very often, this could cause major issues for your program. We're finally at the time where we're ready to formally define what we mean by big O of n. We've been talking about it a whole lot. We've given a number of examples of big O running time, but now we're ready. We've seen enough algorithms that we're ready to do this a little more formally. And I think this is the most formal the mathematics gets for the class, and don't worry if a little bit of this goes over your head. It's mostly here for your edification and enjoyment the day before your mid-semester test. So, big thank you to everyone who's pointed out my mistakes on various slides so far. Keep it coming. And the same goes for today as we do 1 or 2 derivations in the time that remains for us. What we're going to be looking at for O of n is the rate of growth of our functions. So we don't actually care for the purpose of the mathematical analysis exactly how many seconds it's going to take our program to run. What we care about is broadly how does the function behave. To do this, we're going to consider the entire universe of all the functions in the world, every single possible function. So if you think of like 3x squared plus 2, that's in that set, or 100x to the power of 99 plus 7x to the power of 3 plus 2x log 5, all of those things are in the set of every function. So imagine you have a giant infinite-sized box, and inside the box is every single possible function. That is the starting place for our big O analysis. Now let's take all of these functions. Let's say that these are functions parameterized in one variable x with n, which is going to be the size of our problem. So the size of our problem we might measure in how many items in the array, or how many bits in our in the number that we give in, whatever it happens to be. Let's now divide up all of these functions in our infinite box, depending on how long it takes them to run based on the input. So if the function takes a really, 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 really long time to run based on the input, it will be in one pile. And if the function takes only one step to run, no matter what the input is, it'll be in a different pile. Now let's take the simple example of a function that only ever takes one step to run. There are a lot of functions in this. So for example, f of n equals 3. Something that always takes exactly three steps to run is going to be in one pile. And let's say it always takes 5 steps to run. We're going to put it in that fast pile as well. 7 steps, also in that pile. All the things that take a uniform number of steps, no matter what the input is, that is, they don't rely on the size of the input, we're going to put them all in the same pile. And this kind of breaking up our functions into different piles is going to be how we define big O. Big O is saying, is this pile a faster pile than some other pile? Is the function that you are looking at in a faster pile than the functions that it is big O of? So if something is big O of n, that means the pile of functions, let's call this function f. F is big O of n. The pile of functions in which we put f is a faster pile than all the functions that run proportional to the length of the input being n. So we have our faster pile and our slower pile, and we're saying that our function belongs in the faster pile. And we'll get this in formal notation now. This is the way we'll capture it. Our function f of n is big O of some other function g of n if and only if, long confusing statement. Let's break down long and confusing statement. If for all values of n larger than some threshold, so once our problem is large enough, if for all values of n large enough than some threshold n0, so once our problem is bigger than n0, there has to be a multiplier c that proves that our function is always going to run faster than any of the functions from the slower class of functions. So our pile, our individual function belongs to a pile of functions that after some threshold is going to run faster than any of the functions in that other pile bounded by a multiplier c. And we've written this formally. There exists some threshold value, so once there exists some size of problem that's large enough, and there is some multiplier bigger than 0. This backwards e symbol means exists. So there exists these two numbers such that for any bigger problem, once the problem gets bigger than n0, our function is always going to take less time to run than any of the functions from the larger pile. Correction, larger than the representative function from the larger pile. So if c is 2 and g of n is, we'll do a concrete example, that'll be an easier way. This is pronounced of g of n or order g of n are two equivalent ways of saying the same thing. One warning here is that as soon as you pick your values of the threshold and the multiplier, you have to stick to them for the rest of the proof. The intuition here is that we're going to ignore when the problem size is really small, because if we're only searching an array of 3 items, it's not really going to make a difference which of these two ways of searching through the array or sorting the array are faster. The problem size is really small. But we're looking for some threshold size when the problem becomes big enough that this starts mattering how the functions really behave. And the behavior of the functions is probably going to stabilize after the problem size gets big enough to some multiple of the bigger function. Here's a simple example. Let's take f, the function that we're actually looking at, is 2 of n. We can say that is 2 times n. Then we can say that 2n is order big O of n for all values, where n is bigger than 1. 1 is our threshold value, and c is our multiplier 2 here. Let's do an actual proof of this one. So what we're trying to prove is that there exists some threshold once the problem is big enough, and some multiplier c such that we know that there we go. Such that we know that 2 of n is less than or equal to our multiplier c times n. So what we're looking for, 2n. So I'll erase that. for when some multiplier c that we can find to make this always true once n is bigger than some threshold. So in this case, let's pick c is equal to 2. Let's just argue this and see if it works. So if I set c equals 2, then I have 2n is less than or equal to 2n. When is this true? How large does our problem have to be for this to be true? It's always true. So as long as, let's pick some value of n0, and let's set n0 equal to 1. And so it's always the case that 2n is less than 2n, even for n0 equals 1. So there is our overall sketch of the proof. We know that this is correct because we have found a value of c and a value of n0 such that this statement here is true for all values n greater than 1. So there, this gives us our final line. There exists a c and an n0 greater than or equal to 1 such that f1, which we can just replace by 2 of n, is less than or equal to c of n, and we know that c of n was 2 and our n0 was 1.
No one knew what that was about.
Perhaps someone on Zoom. Anyway, so there is our simplest big O proof. And with that, I think we will, we've got one more slide to go for today, and then we'll cut off early, slightly early, so that all of you can take a few minutes breather and study up for the mid-semester test. One important thing here to note is that because of the way we've defined big O, we can talk about any pile of functions that are slower than our function, and we're still big O of them. Remember, if we're in the super fast pile, and there's a slower pile here, there's also another slower pile here and an even slower pile here. So if we say that 2n is big O of n, 2n is also big O of n squared. It's also big O of n cubed. It's also big O of 2 to the n. All of those piles of functions are bigger, take longer to run than our initial function, and so our fast function is big O of all the classes of slower functions. And while we'll talk a little bit in the next lecture about tightness of bounds and why we might care about this, but this is the general intuition. We're just saying what things our function is faster than, and it's faster than a whole lot of things. And with that, good luck for your mid-semester test. I will catch you all in a few days. When the mid-semester test is done, shoot me an email, let me know how you're going, and please take a bit of a rest. And I will see you all next Tuesday.